Hi everyone. Welcome back to the final papers and closing session of EGPGV. In this session, we'll have two interesting talks on visualization of particle data, followed by the symposium closing. So the first talk is on UnityPIC, Unity Point Cloud Interactive Core, and it will be given by Yaocheng Wu.
Hi everyone, my name is Yaocheng Wu. I'm a second-year PhD student at the CUNY Graduate Center. Today I will be presenting our work titled UnityPIC, Unity Point Cloud Interactive Core. My co-authors are Dr. Hui Vo, who is a professor at CUNY Graduate Center, the City College of New York, and CUSP NYU. Dr. Gong, who is a professor at Rutgers University, and Dr. Zhigang Zhu, who is a professor at CUNY Graduate Center and the City College of New York. Our work proposes a point cloud rendering pipeline in the form of a Unity component. To improve the performance of the pipeline, we've proposed two algorithmic improvements. Then the resulting rendering pipeline is evaluated in the context of interactive visual quality. We recognize that a scalable visualization pipeline is a shared commonality amongst interactive point cloud applications, which means it can be generalized. There is motivation to do so because it is time-consuming to develop, and the developed pipelines are usually written in low-level code, which lacks portability across development and production platforms. This is also the reason why Unity was chosen as the platform, because Unity projects are highly portable and Unity can export to a wide range of production platforms. Another motivation of our work is that high-resolution point clouds need to be rendered using high point budgets in order to capture the fine details. Also, new technologies like VR and AR have higher rendering requirements, and some applications may require multi-view rendering or other more advanced multi-pass rendering algorithms. Therefore, we seek to improve the overall rendering performance of the pipeline. The proposed rendering pipeline follows the standard pipeline, which includes the three processes: traversal, loading, and rendering. We've also added an extension to allow the processing of data upon arrival or removal. Our work adopts Poultry's file format because of its scalability and accessibility. They provide an open source converter that supports conversion from a wide range of point cloud formats. In order to improve the overall pipeline, we've proposed two algorithmic improvements. First, to address the adaptive point sizing problem that comes with hierarchical point cloud structures, we've proposed a dynamic batching algorithm to generate a new internal data structure more suited for rendering. To improve the rendering speed, we proposed an approximate rendering algorithm. Here are some existing works in the past. QSplat was the first point cloud rendering application that used a binary tree as its level of detail hierarchical structure. However, it was slow because of the division of the point cloud, and it continued until there was a single point left. Sequential point trees are arrays of points optimized for GPU rendering. The points are ordered such that only a prefix of the array is processed when rendering in order to achieve a certain level of detail. Layer point clouds introduced the first object space point clouds, where the nodes in the hierarchy contain a collection of points rather than a single point. So the lowest primitive in layer point clouds is a small subset of the points rather than a single point. Nested arc-trees are arc-tree structures where each leaf contains an optimized version of sequential point trees. Their proposed application is called instant points. Modifiable nested arc-trees are nested arc-trees with a data manipulation interface. Lastly, Poultry is a web-based point cloud rendering plugin. They introduced a file format which extended the scalability of the out-of-core structure by formatting the hierarchical metadata into chunks that can be loaded on demand. In addition, they introduced the first GPU-based solution to the adaptive point sizing problem. The hierarchy traversal process mainly performs custom calling. The traversal process usually follows a priority metric. In our pipeline, we simply use the estimated projected area through perspective projection. Also, we weighted the priority to allow more points to be rendered towards the middle of the screen, as well as more closer points being rendered. These weights can be configured via a user parameter. The figure here shows that from top to bottom, the center becomes more focused, while the borders become less focused due to the adjusted user parameter. The main focus of the proposed dynamic batching algorithm is to solve the adaptive point sizing problem. The main challenge to achieving adaptive point sizing is that the points within a single node may need to be rendered with different point sizes. This poses problems in real-time rendering because this configuration can be different every time depending on the viewer's position and orientation. Take the green node for example. Its points span across 3 different resolutions and therefore it needs to be rendered with 3 different point sizes. The only solution in this case is to compute the point sizes on the fly. As mentioned previously, Poetry's approach was to upload the hierarchy information to the GPU and then compute the point sizes in the vertex shader by traversing that hierarchy. Our proposed approach is to allow points to inherit points from its ancestors. By this process, when rendering a node, the rendering of the points that belong to higher resolutions can be delegated to the descendants. In addition, the points are partitioned by the octants they belong to so they can be accessed easily. The resulting rendering now looks like this. You can see that the green node no longer needs to render to the bottom quadrants. The children nodes also contain those points that can account for that rendering. As a note, in comparison to Poetry's GPU-based method, our proposed scheme acts as a pre-processing step rather than real-time computation of the point sizes on the fly. The main benefit of the dynamic batching scheme is the simplification of the rendering process in order to achieve adaptive point sizing. Also, the proposed scheme improves data access, since accessing the points within the bounded region can be achieved by accessing one node rather than all the nodes along the path from the root to that node. The drawbacks are, of course, the additional CPU bandwidth used for processing and then the increased memory usage to store the duplicated or inherited points. The time complexity of the algorithm is O of n, and thus the asymptotic complexity of the point loading remains the same. Also, this increase is not noticeable due to loading largely being I/O bound. For the memory increase, our analysis hypothesized an increase of about 33%. And later when we perform experiments, the empirical results also showed a similar increase. For the experiment, we followed a camera path of roughly 2,000 frames and captured the original point count and the new point count after dynamic batching. In the graph, augmented refers to the new point count. And the percentage change is computed for each frame, and you can see that it remains roughly at 33%. After dynamic batching, the rendering of the points now requires a test to check whether a point should be rendered. We summarize that information into a single mask for each node. We define the occupancy mask to keep track of the octants that contain points, the visibility mask to keep track of the visible octants or children, and the inheritance mask to keep track of which points have been inherited. The final render mask is computed as the logical AND of the visibility and inheritance mask. In other words, what this means is that a point is only rendered if it is visible and not inherited by a child. So this ensures that only a single copy of each point is rendered. As an example, if you look at the green node and then its defined masks in the table, the last 2 bits of the inheritance masks are set to 0. Those bits correspond to the bottom quadrants, which have been inherited by its children. The resulting render mask for the green node is 1100, meaning that only points in the top 2 quadrants are rendered. Moving on to the approximate rendering algorithm, the goal of the approximate rendering algorithm is to reduce overall GPU shader operations. The original rendering pass is simple, which is to generate a quad for each point and render the quads. Now, this process can be wasteful if you consider the typical point budget and then the typical number of pixels available on the screen. Say, for a 5 million point budget rendering to a full HD screen, there are only 2 million pixels. So that means at the maximum, 2 million points can be represented at once. So, but in the original rendering pass, 5 million points would be rendered instead. The proposed algorithm uses an intermediate pass for approximate occlusion culling. First, the points are rendered as pixels to an intermediate texture. Its XY click positions, color, and radius are stored in the RGBA elements. The second pass will read from the intermediate texture and treat each pixel as a single point and perform normal rendering. So essentially, for all the points whose center renders to the same pixel, only the frontmost point is taken. The frontmost point is assumed to occlude every point behind it, and thus only one point is rendered. We've summarized the possible errors generated from this approximate occlusion culling. First, the occlusion error occurs when a smaller point occludes a larger point in the first pass. In this case, any information beyond the radius of the smaller point is lost, when in fact, a part of the larger point in the back is still visible, but during rendering that will not be shown. The intrapixel error or rasterization error occurs when 2 points of the same size are rendered to the same pixel. The slight difference in their positions within the pixel can cause differences in the rasterization results. We've performed experiments to assess the degree of error sustained and the performance increase across a range of point budgets. And the error metric used is the mean pixel error, which is simply the average pixel difference across all pixels. The experiment showed that the error converges after about 40 million points to 7. The maximum value of a pixel is 255, so that is about roughly 2.7%. In contrast, the performance gain is much more significant. We can see a roughly 75% FPS increase at 10 million points and a 120% increase at 20 million points. In addition to the global error that we observed, we also wanted to see how the errors manifest locally in different scenarios. Specifically, we use the difference evaluator flip to generate difference images for a top-down view and a grazing view. The top-down view shows the errors being distributed more uniformly across the rendering, while the errors in the grazing view are more concentrated around the faraway points. This concludes that the degree of errors correlates positively with the amount of occlusion. More occluding points will generate more errors. Finally, we conducted experiments to showcase the interactive performance as well as the visual quality during interaction for our rendering pipeline. The experiments are conducted across 2 different data sets, Dublin City and New York City. The Dublin data set contains 1.4 billion points, and the New York City data set contains 22.8 billion points. For each experiment, a camera path is followed, and then the following are captured for each frame. The actual rendering of the frame, the point count, and then the FPS for that frame. The capture renderings are compared against a high-quality baseline generated with 300 million points, and then the mean pixel error metric is used to summarize the differences in comparison to that baseline. Due to the high point budgets we use for the experiments, which are 10 million and 20 million, we used high quality blending as the default rendering technique. High quality blending has a higher capacity to represent larger number of points because each pixel is a weighted average of all the points that fall within a certain range. So essentially, high quality blending also has the effects of anti-aliasing. For the purpose of comparison, the results for with and without approximate rendering, or in the graphs it's called delayed expansion, are both included. On the left, the interactive visual quality shows the mean pixel error across all the frames. The mean pixel error is in general maintained below 30, meaning there is a maximum of about 12% difference overall. The additional error introduced by the approximate rendering is less noticeable for 10 million points and much more noticeable for 20 million points. In the middle, we can see that the point budget is mostly fully utilized for 10 million points. However, it is more difficult to maintain the full point budget for 20 million points. We can see that from this we can see that the IO bottleneck is reached at somewhere between 10 million and 20 million points. On the right, rendering pipeline overall maintains interactive FPS for both 10 million and 20 million points. However, you can see that the performance gain from the approximate rendering is very significant. And here is a video demo of our work. This research is supported in part by the National Science Foundation Award and Alfred P. Sloan Foundation Award. Additional support is provided by the Air Force Office for Scientific Research, the Intelligence Community Center of Academic Excellence at Rutgers University, and the Vingroup Innovation Award. Thank you.
So thanks you, Yaocheng, for that very interesting work. So please post any questions on the Discord, but I will start off then because I have a few. Yeah, one question I had actually, since the work is in Unity, as Unity is getting to be more popular, even beyond games, as like for sci-vis or VR use cases, I was curious if you were planning to release this openly, available as like a plugin or open source that people could use in their own Unity projects.
Yes, we are planning on releasing it, but not yet because there's still some finishing touches that needs to be done currently.
Okay, and then let's see. So I do have one other one that I was kind of curious about for the approximate rendering step, where you render the particles as points to the screen. I was curious if it will depend somewhat, I guess, on how many particles are visible. But if you would think maybe if it would potentially be worthwhile to have some, or if you were already doing some kind of compaction step, or if the second pass to render them as points is like a full screen pass over the pixels, where you render each one as a point, or if you compact them to, say, like filter out inactive pixels, essentially.
The first pass already acts as a filtering step where essentially any overlapping point is deleted, only the frontmost point is taken. So I don't think there's any more compartment. And I don't think you can make it any more compact for the second pass, because you're essentially just taking each pixel and treating them as a point and just directly rendering them.
Okay, so if there are no more questions, we'll move on to the next talk here. So our second talk is on interactive selection on calculated attributes of large-scale particle data, and the talk will be given by Benjamin Wollet. So let's see the talk.
Hello everyone, I am Benjamin Wollet, a PhD student at the University of Stuttgart and Kooperatives Promotionskolleg Digital Media at Hochschule der Medien. In the following 20 minutes, I'm going to demonstrate our work that creates the missing connection between derived field generation and region growing within particle datasets. As a start, let's take a look at one example of a particle-based simulation. You're now watching a part of a fluid simulation consisting of 10 million particles. The scenario shows a dam break where the fluid hits 3 towers. Although there are only particle positions present in a scenario, we can use our solution to lazily evaluate attributes limited to the manually selected particles and to the extended region, which are the particles directly under the surface of the fluid here. By keeping the selection, we can now track down the flow of the particles during the rest of the simulation. As we are evaluating the attributes only when needed, we are able to reduce memory consumption and computational time, especially for real-time applications. But why can't we just store attributes during simulation time, or derive the attributes we might want to visualize beforehand? Well, we don't persist these attributes during the simulation because of limited disk space. Sometimes we don't even know the required features until the simulation is completed. This happens especially when we are searching for errors within the simulation or when we are evaluating new techniques. In most cases, we only need a small spatial or temporal subset for the analysis, so we don't need to generate data for the whole simulation domain. Additionally, while the effect of such an error is visible within the simulation, a manually selected subspace is often wrong, because the cause of the error might be connected, but through several connections in another region. It can be hard to guess a working and static subset and keep a limiting bounding box small. This is where region growing comes in. Prior work has already pointed out the need for interactive selection within attributes using linked 2D and 3D views with logical combinations of attributes. There are spatial and temporal correlations as a basis for new attributes, and multi-core solutions of derived field generations are part of today's production tools. We have them available in ParaView and Visit, for example. Quite recently, deriving attributes has been completed by just-in-time compilation, which helps us to define the required attributes as late as possible. The field of region growing has recently been used to assist the distinction of fluid and rigid bodies for simulations on the GPU. Acknowledging the spatial and temporal correlation of similar attributes, region growing can assist us as a dynamic selection method. It can help us to find relevant areas within the visualization dynamically. By combining the two features, region growing and lazy attribute evaluation, we can reduce calculation time and save memory in real-time analysis tools. To get an impression of how our method works, let's start with an overview of the user workflow. All starts with selecting regions of interest, which we have to select manually by brushing. The selected particles are illustrated in green color in the first picture. Next, you have to choose an attribute to calculate and a comparison function. Typical comparison functions are extend to maximum values, to bigger values, or to similar values. When you now start the extension, all required attributes are lazily evaluated and the extension is executed. You can see the particles chosen for lazy attribute evaluation marked in red in the second picture. As one extension step is not sufficient in most cases, you can repeat extensions automatically several times. For example, similar density values on the surface create the illustrated results for the multiple extension steps on this slide. To examine the results in more detail, our rendering engine can hide unselected particles. Additionally, you can observe subsequent time steps when starting playback within a time series. This is shown as an example in the last picture. We are moving on from the user workflow to the technical flowchart. Aside from one setup and import step, our method is split into 3 execution phases. The setup and import phase builds up necessary data structures and imports the manually selected data into the workflow. It then triggers the first preparation phase with information about the cells and all the neighbors we need during the first extension. During the following preparation phase, we evaluate the attributes for all neighboring particles. Attributes are evaluated by cell, and each cell is evaluated only once, considering overlapping neighbors between cells. To enable the extension of particles within the cells marked in red in the second picture, all white cells need to have attributes available and all green cells need to be accessed. Now we can run the actual extension with all necessary attributes already available. We execute this phase repeatedly in parallel, and as the extension is not independent of other extensions, this phase is followed by a consolidation. The parallel execution is illustrated as a top and a bottom branch here. The upper and the lower part in this example first select a particle within the same cell, then extending to a neighboring cell. Particles selected by a particle within the same cell are defined as internally selected, while particles selected in other cells are defined as externally selected. Please note that each neighboring cell, which is highlighted in red in both last steps of the extension, is the same overlapping cell in a global context. This is why in the consolidation phase, we need to find out which cells are a source of the following extension and which attributes are needed to execute it. If necessary, we initiate a loop to continue the extension. To exchange information between the different phases, all phases share a scalable work buffer of cells. I already mentioned additional data structures being necessary to execute this method. I will now give you an introduction to them, together with some design decisions we took for our solution. For region growing and attribute evaluation, we need a solution for neighbor search. We went for a regular grid of indexes as spatial decomposition. Despite this decision, our solution is adaptable to any index-based spatial decomposition with an appropriate but potentially more costly neighbor search. The grid structure is created once during this setup phase. It sorts the particles' indexes into the cells by applying a Z-curve hash. In our example, particle 5's position is hashed and results in its index being put into the cell 3. As we only require all particles being found by cell, the order within the cell is not relevant to store this information. We use this opportunity to subsort the particles' indexes in a cell by their selection states. A particle can either be unselected, latest selected, which means selected during the latest iteration, or selected. The selection states define this particle as the possible target of an extension, the source of an extension, or completely uninvolved if already selected. In our example, particle 5 has been selected during the last iteration and is sorted accordingly. In addition to this data structure for each particle, we introduce a data structure containing information on if a cell needs resorting because particles were selected, which is labeled as. Resorting a cell is necessary to update the subsorting when particles in this cell are selected. Within this static data structure, there is another flag whether this cell needs attributes for an upcoming extension, and an offset where the dynamic information among extension of this cell is stored. As our solution is able to derive attributes from derived attributes, the label consists of up to 3 bits, which means it can store up to 8 attributes. We also introduce a dynamic cell information, which is appended upon the creation of attributes for particles within a cell. It contains the borders for our subsorting into selection states and the information on where the attributes for this cell are stored within our dynamic attribute information. With all the requirements set, let's move on to the method itself. For a more detailed understanding, let's go through the single steps, starting with preparation after we now finish the setup. We aim to keep the memory footprint small, so we use memory only for the cell to get attributes for, which is named the base cell here, and one other cell. This is required as limitations on memory are especially tough to reach when multidimensional attributes are evaluated based on other multidimensional attributes. At first, we work on the base cell before moving on to the evaluation of neighboring cells. We wanted to keep a certain possibility of adaptation in our solution, so there are 2 configurable functions. One is being evaluated for each neighbor with the particle information and the neighbor information and stores back the result for this particle. Then, a reduction function creates the attribute result for the particle. This function is typically a weighted sum or similar. For now, both functions need to be available at compile time, but as previously mentioned, Ibrahim et al. Recently provided a solution for just-in-time compilation being able to solve that limitation as part of their work. When attributes are evaluated from the base cell, the exact same process is executed on particles in neighboring cells. Next in line is the extension phase. As with a lazy attribute evaluation, we only use memory for attributes of the cell which is source of the extension, the base cell in this case, and one other cell to keep a small memory footprint. So again, we extend the base cell first. We select all particles that match the chosen condition within this cell and mark them as internally selected. When additional particles are selected, we resort the cell and repeat to check if this extension creates more extensions within the base cell. This internal and fast repetition helps us to reduce slower repetition cycles in the main workflow. When particles are selected by parallel branches, we can ignore the selection in a future cycle if the particle is also internally selected, as we used it as a source of extension already in this cycle. Subsorting the particles within the cells reduces comparisons and therefore calculations for the next steps, as only particles that have been selected during the last cycle have to be evaluated against unselected particles. As we now extend to neighboring cells one by one, we only consider unselected targets and the latest selected sources for the extension. The procedure is identical to one repetition cycle within the base cell. Nevertheless, particles are marked as externally selected in other than the base cell. At the end of each extension loop, we check if other particles were selected and the containing cell is not already marked with a cell needs sorting flag. Then we add the cell to the work buffer for the upcoming consolidation phase. The consolidation phase is linking region growing from the extension phase and lazy attribute evaluation in the preparation phase. We use it to set up the work buffer for our next iteration. Taking all cells involved in the latest selection as input, we define the sources of an extension for the next iteration and add the cells for which we need lazily evaluated attributes. To do that, we check for particles that were exclusively selected from another cell and move them to the section of latest selected by subsorting the cell's indexes. Particles that are internally selected are directly sorted into the selected section of the cell and will therefore not participate in region growing as a source. As we can use our predefined borders between the separate selection states, we can now easily check if a cell will be the source of the extension and add it to the work buffer for the next extension phase. In this case, we check all neighboring cells for missing attributes using our defined needs attribute flag and populate the work buffer with those cells for the next preparation phase. As soon as we don't have any source cells for our region growing left, the work buffer will remain empty and the loop within the main workflow stops. As we now know how our method works, let's have a peek on how it looks in operation and shortly dive into one of the use cases discussed in our paper before we proceed to the technical evaluation. One of the two use cases we analyzed in our paper is a fluid scenario simulated using smooth particle hydrodynamics. It consists of 10 million particles. The 4 jets creating the inflow contain significant density variances, which result in pressure shocks. These pressure shocks are located inside the jets and can negatively influence the stability of the simulation system. We will now see how our solution can assist in detecting these shocks, although pressure and density were not saved together with the simulation. At first, we select some random particles on the surface of one of the jets. We extend the selection to similar density values and automatically hide the selected particles. During the extension, all necessary density values are evaluated lazily by applying the used smoothing kernel as a weighting function. Now, areas of high density remain visible as disks, the presentation of the pressure shocks we were searching for. This enables us to analyze the position, structure, and possible reasons interactively in more detail. I'm moving on to the technical evaluation. We conducted 2 timing experiments and 1 measurement of memory consumption. During the technical evaluation, we used a fluid scenario scaled into 4 different sizes from 640,000 to 80 million particles. In the first experiment, we randomly selected 1 particle in the fluid and extended the selection until all particles were selected while lazily evaluating the density. We repeated the measurement 100 times, choosing different particles as a start particle, and measured the time to select 1 particle during the extension. For each scenario, the median as well as interquartile boundaries P25 and P75 are plotted. There are 2 main observations. First, the time needed to process 1 particle is almost independent of the scenario size. When more particles can be selected at once, the performance even slightly increases. Additionally, we can observe that the variance increases in small scenarios when almost all particles are selected. Apart from this observation, we measured a low variance throughout the whole extension process, which leads to the conclusion that the choice of the starting particle does not influence the performance. In our second timing experiment, we measured the performance of our 3 recurring phases separately for the fluid scenario with 80 million particles. Again, we randomly selected a particle to start and executed 100 repetitions, plotting the median and interquartile boundaries. In addition to our lazy evaluation, we performed region growing after calculating all attributes upfront. The timing result is plotted in gray and is to be compared to the sum timing plotted in orange. Again, we can see the low total variance between the repetitions with different start particles. Seeing the timings of our different phases plotted separately, it is clear that our main coordinating phase, which links the 2 techniques region growing and derived field generation, is almost neglectable in comparison to the 2 worker phases. As it adds little to the overhead, It's obvious why the lazy evaluation outperforms the pre-calculated solution until almost 90% of all particles are selected. Breaking it down to the necessary computation, this is an expected result, as expensive operations like the neighbor search or the attribute calculation itself are executed the same way, only in a different order. Our last measurement is about memory consumption. Again, we used the fluid scenario with 80 million particles, which has an average cell occupancy of 13%, and compared it to the pre-calculated scenario. As we are building our data structures on top of a regular grid, the cell occupancy directly influenced the number of cells and therefore the memory usage in comparison to the static approach. Other main influences are the number of dimensions, the number of attributes that are evaluated, and the number of particles that can be extended within one repetition cycle. For the chosen scenario, we varied the cell occupancy from 13 to 75% by resizing the cells and measured from 1 one-dimensional up to 8 three-dimensional attributes. In this figure, the memory usage, depending on the percentage of attributes selected, is plotted. As a result, we are able to reduce memory consumption with the exception of almost all particles being selected. The memory consumption is reduced by up to 80% with an average occupancy of 75% and 8 three-dimensional attributes, which is the current limitation of our solution. In the past 20 minutes, we presented a solution that combines region growing and derived field generation to evaluate attributes lazily. After explaining our choices on general requirements, we elaborated on the use technique and its implementation details. We showed its application in 2 video sequences. We confirmed that our solution outperforms pre-calculated attributes in terms of computational time and memory consumption for the intended use cases by 3 separate technical evaluations. We therefore see our method as a helpful extension, especially for use in real-time visual analysis tools. If you have any questions on the presented method, feel free to contact me. You will find updated contact details provided on my ORCID page. To conclude, I would like to thank Promotionskolleg Digital Media, Hochschule der Medien, and the University of Stuttgart for enabling our research, and our audience for listening.
So thank you for that interesting work. We'll thank the speaker here and open up for any questions that we have from the audience. But I will start with one question that I had. So one thing that I thought was interesting is that the different computational steps are very localized on the GPU, so that each cell is processed independently, and then you have this consolidation step. And so I was wondering, in the case of very large data that may not fit on a single GPU, what you thought about possibilities of extending this to maybe like a streaming approach or a distributed approach to handle these kind of very large data sets.
Yes. Thank you for the question. In fact, we didn't think about this too much for the moment. It was really like reducing data sets that fit on one GPU and kind of reducing the time that that is necessary for calculation. Of course, it is possible if you have the possibility to kind of isolate parts within the spatial domain. Of course, then it's possible to kind of create subsets that fit then once again on the same card. But otherwise, yes, of course, there might be some kind of a streaming solution that you can use a kind of a dedicated card, especially for calculating the attributes and performing the region growing in several regions. Yes.
Yeah, very interesting. So yeah, I'll have one more question then. So one thing I thought was interesting too is on the first scaling experiment, and I guess maybe it's a little hard to see without the slides back up, but the time is decreasing and then starts to increase again a little bit as you get to a very high percentage of particles selected. And I thought that was interesting, that it would actually start to take like longer to pick one particle. I was wondering if you could elaborate on that a little bit.
Yes, this is of course kind of part of the scenario, because we were selecting one particle and then extending the selection to having more and more particles selected. So when you're coming to kind of the end of the possible selections that you can make, then you have not the same amount of particles that you can choose from for extending the selection. So it's kind of, you're coming kind of into a saturation, and this of course reduces the possibility of selecting particles, because especially on the ends of the simulation domain, you have the problem that there are no more particles to select. So it's not kind of, as we're measuring the time to select one particle, of course, then as you have less particles that can be selected, then you kind of get back into a phase where time per particle increases again.
Yeah, that's quite interesting. Yeah.
Yes, I think this is really kind of this is a problem, but I mean, this is not kind of the intended use case that we have almost all particles selected. The method is especially designed for creating small subsets of large particle data sets. So, of course, we measured it, and it is a problem, in fact, that when you have more particles selected, that you get into this again increasing time to select one particle. But of course, this is the part where the method again, it has problems with memory consumption as well in this part, because this is not what it has been designed for. It's really like only creating smaller particle data sets from large data sets.
I see. Yeah. Cool. Okay, so we'll thank the speaker again if we have no more questions. So thank you, and we'll thank Yaocheng as well. So thank both the speakers in this session again for two very interesting works. And we'll move on to the closing.
Thanks for having me.
Yeah.
Hey, I'd like to welcome everyone to the Best Paper Awards and the closing remarks for EGPGV 21 on behalf of Markus, myself, Filip, and Amani. So just to remind you of the review process that all the papers went through, we had short papers that were up to 5 pages, including references. We had full papers, which were 8 to 11 pages, including references. And we had 2 entry points. As we had for the last couple of years, we had an early submission deadline, which was due in December, and a regular submission deadline that was due in March. And so, the early submission process has been very, very successful, and it provides us an opportunity to shepherd papers through several revision phases to successful submission. And we had 4 independent reviews for each submission. So of the accepted papers, we had 3 short papers and 5 full papers. And really the mission of EGPGV is to provide a platform to exchange, experiences and knowledge regarding new methods and trends in parallel graphics and visualization. So, the topic has been growing in importance due to hardware trends and computationally demanding applications in computer graphics and visualization. This requires efficient usage of multi-core CPUs, GPUs, and clusters. So accordingly, EGPGV seeks papers on graphics and visualizations that involve any type of parallel computing and focus on very large data sets in addition to computer graphics. So this year we have two Best Paper Awards, 1 full Best Paper, which is what we traditionally award, and we have 1 Best Short Paper, which is new this year. So this year, the Best Paper Awards Committee consisted of Ulf Asserson, Hongki Guo, and Ingrid Holtz. And so we'll start off with the Best Short Paper Award. And the Best Short Paper Award goes to Robo Benhib, Dave Pugmire, and Hank Childs for their work of a high-low pod, the parallel particle advection via hybrid of lifeline scheduling and parallelization over data. And so the committee remarked that they like this paper because it provides sort of a best of both worlds approach to particle detection with very large data sets. So congratulations to Roba and all the other co-authors. And so our best full paper award now. And the best full paper award goes to Sudhanshu Sane and all of the numerous authors for scalable in situ computation of Lagrangian representations via local flow maps. So the committee was impressed with the simplicity of the communication-free approach. It was a well-written paper and provided a thorough analysis and a theoretical error analysis as well. So congratulations, Sudhanshu. And so in closing, we're looking forward to EGPGV 22. Hopefully this is not going to be a virtual event again. I know we're all looking forward to getting out and seeing each other in person and traveling. And for EGPGV 22, we're looking to continue to expand our community. Things that have been a success over the last couple of years has been, we've had a student program chair. So again, thank you, Amani, for being the student program chair this year. It's been a big success, and we'd like to continue to do that. Likewise, the early submission process has also continued to be a success. With all 6 early submission papers this year were accepted into the program. So I think it's been very successful, and we'd like to continue to do that. And of course, your feedback and input on the program is welcome. So please don't hesitate to contact any of us with your feedback or input. And finally, I'd like to thank everyone again. So thank you to all the authors for submitting to EGPGV. Thank you to the program committee and everyone for their service that made this possible. And I'd like to thank everyone who attended EGPGV. So thank you very much for attending, and hopefully we'll see you next year.